Hello, in this chapter we will be covering aromatic substitution reactions. We've already seen how aromatic pi bonds are less reactive than your typical alkenes. Here we have an example of your typical alkene in a cyclic system and a bromination reaction, whereas if this alkene were part of an aromatic system, that reaction would not proceed. However, when you add different species, such as iron in this case, a substitution reaction does happen. The observed reaction is what we call an electrophilic aromatic substitution. This is going to be one of the focal points of this chapter. We're going to use the shorthand notation EAS for electrophilic aromatic substitution. And what that is an aromatic proton is replaced by an electrophile. The ring will be acting as a nucleophile, in which case you have a few examples here. You can add halogens, for example, nitro groups, among others. The aromaticity of the ring is preserved. That's the key concept involving electrophilic aromatic substitution reactions. Let's talk a little bit about halogenation. In the bromination of an alkene, bromine functions as an electrophile. We call it an electrophile because even though the species is considered nonpolar, it does have that London dispersion factor that gives it some slight positive, slight negative, short-lived polarity, and that is enough for it to behave as an electrophile. Electrophile, electron loving, right? So that means that it is positively charged. A Lewis acid catalyst is needed to make bromine electrophilic enough to be attacked by the more stable p electrons of an aromatic ring. That's where the iron atoms come in. As you can see here, iron interacts with bromine, making iron 3 bromide. Iron 3 bromide then activates the bromine, making it even more electron poor, in other words, more electrophilic. So it's not just the London dispersion force, it's that separation of charges that you get by interacting with iron 3 bromide. The mechanism for this type of reaction follows the steps delineated here. First one is going to be the aromatic ring attacks the electrophile, sigma complex intermediate is activated. So here you see the nucleophilic attack plus loss of a leading group. You can see the attack here of that pi system to the bromine, and then those electrons migrating. And here you have what we call the carbocation that is raised and stabilized. We're going to call that the sigma complex. This is a term that you're going to see throughout the chapter many times. So basically sigma complex is when you have a resonance stabilized carbocation. So once you have that, then the next step is a deprotonation of that sigma complex, giving you the re-aromatization. So in other words, you start off as an aromatic, you end up as an aromatic, right? That's the key concept that we need to familiarize ourselves with. Addition reaction to an aromatic ring would be endergonic. So it requires energy, it absorbs energy, which is why instead of the addition, you will be seeing a substitution instead. As you can see, just looking at those energy profiles, substitution is going to be much more favorable than your addition instead. Aluminum tribromide could also be used as a Lewis acid catalyst for the bromination of benzene. So in other words, you don't really need iron, you could be using aluminum instead. Same exact mechanism, right? That metal still providing that positive charge, still getting that interaction, more electrophilicity, etc. Benzene can also undergo chlorination, so it's not just bromination. However, when we deal with fluorine or iodine, then it really doesn't work well. And fluorination is really a very high energy, violent type reaction, so it doesn't really, it's not something that we have a whole lot of control over, so it's not really practical. And iodine, being as large as it is really slow to react, and the yields are not really practical. They're very low. So these reactions are, for all practical purposes, limited to bromine and chlorine instead. Note that the electrophilic aromatic substitution mechanism for chlorination is literally the analog that you saw for bromine. So you have the nucleophilic attack, loss of the leading group, formation of the sigma complex, and then the return of your aromaticity. So it's exactly the same thing. If you know one, you know the other. Just change the bromine for the chlorine instead. In fact, all of your electrophilic aromatic substitution reactions are going to be following the same mechanism. So you'll see me, or you hear me, right, discussing different types of mechanisms, but they all involve the same scenario. You lose your aromaticity, you form your sigma complex, and then you re-obtain that aromaticity. That's pretty much it. Sulfonation is a separate type of reaction, right? No longer halogenation. In this case, we're adding sulfite as the electrophile and sulfuric acid as the acid catalyst. Notice that it says here fuming, right? Sulfuric acid. Typically, what that means is that you're having very, very high concentrations, almost completely pure, 97, 98% sulfuric acid. In these cases, you are going to get that sulfite in the form of a gas. Your sulfide is a potent electrophile. The sulfur atom has a significant partial positive charge due to inefficient pi overlap with the oxygen atoms. This is actually very interesting. It's one of those cases where the size of your different elements make a big difference. Sulfur is much more voluminous, much larger than oxygen. So even though we're talking p orbital to p orbital, there's not really enough overlap because of the size difference to generate an efficient pi system. So as a result, that sulfur-oxygen bond has a significant single bond character. So it's going to be a little bit longer than you would expect. It's going to be also a little bit weaker than you would expect. That's important. When you look at the sulfonation, you can see same exact steps as we saw for the halogenation. Nucleophilic attack, the aromatic ring functions as a nucleophile, forming the carbocation, sigma complex, and then you deprotonation. Now, in this case, it's going to be a little bit different because you're going to add a protonation step, right? So you have an acidic media, very low pH, so you have a lot of hydronium. Hydronium, once you have an oxygen in the form of anion, it's very easy for a proton, right, for it to attack a proton of the hydronium and become protonated. Right? That's how you add that sulfur group that we're looking to add in the sulfonation process. Now, this reaction is concentration dependent. So what that means is that if you have high concentration of sulfuric acid, you are going to proceed with the sulfonation. But if you have low concentrations or dilute sulfuric acid, then the reverse reaction is the one that takes place. Now let's talk a little bit about nitration. Nitration happens by using nitric acid as the source of the electrophile and sulfuric acid as the catalyst. So this is a reaction that I'm not a fan of it because you need to have sulfuric and nitric acid mixed in together in very high concentrations. So when you're in the lab, that type of mixture is a little bit dangerous. But it also allows for the formation of nitronium ion, which is going to be the active electrophile in the nitration reaction. So as you can see here, we have the process for the formation of your nitronium. You have a protonation step, right? The OH here, the hydroxyl group, not a really good leaving group, but then it does attack a proton for the sulfuric acid, and now you have H2O, which is a fairly much better, right? A much better leaving group, and that leaves you with the nitronium, which is the one that participates in your nitration reaction. Nitronium is highly electrophilic, right? So always looking for that positive charge to go away, and it will do so through an electrophilic aromatic substitution process. Now here, so you can see, no surprises, right? Same exact process, nucleophilic attack, formation of your sigma complex, deprotonation and return of aromaticity. A nitro group, once you add it, can then be reduced to form an amine. This is actually very interesting because now you have the ability to add a nitro group to an aromatic system, and subsequently you can add an amine to that group, right? You just modify the nitro into the amine, and from there you can then functionalize further into whatever you need, right? So this actually opens the door to a series of processes that the applications are vast. There's a lot of them. Combining these reactions give a general process for installing an amino group on a benzene ring. So you start with your nitrations. You can see here, you add iron or zinc, and you add hydrochloric acid, and then a strong base. And from there, you get a reduction of your nitro into your amine. Let's talk about a friedel crafts alkylation. So you're adding an alkyl group, right? That's what the name suggests. Alkylation occurs by using an alkyl halide as the electrophile and aluminum chloride as the Lewis acid catalyst. So in that sense, you're adding, right? In this case, for example, you're adding this group and you're using the aluminum chloride as your acid catalyst. The result, you add an alkyl group of your preference, whatever that is. The catalyst functions as you would expect. You see an attack between that chloride and the aluminum. It makes it a much better electrophile, which would then proceed to move and generate your carbocation as you would expect. The alkylation mechanism, very similar to what we've seen, the main difference being this step right here on top, the formation of the carbocation. The interaction between the alkyl halide and the aluminum chloride, that's going to be the main difference. That's what I would like for you to focus on at this point, since everything here on the bottom is pretty much we've seen at least 3-4 times already. Nucleophilic attack, loss of aromaticity, formation of sigma complex, and then reformation of that aromaticity. Simple primary halides can be used very effectively, and there's no steric hindrance, there's no other steric or kinetic factors involved in your simple primary halides. Since primary carbocations cannot really form, then the electrophile is presumed to be a complex, right, which we see as your adducts when we're talking about Lewis systems. So similar to that, that's the complex that we're talking about when we talk about electrophiles in primary halides for Friedel-Crafts alkylations. However, most primary alkyl are susceptible to rearrangement. We've already seen that from our organic one. So therefore, you could expect a rearranged product, right? That's not out of the ordinary. You have from your primary to secondary or tertiary, if possible, and that'll happen. And as you can see, you're going to have a mixture of isomers if the rearrangement happens, which is likely to happen. There are 3 other limitations to the Friedel-Crafts alkylation. First, the halide leaving group must be attached to an sp3 hybridized carbon. If it's something like an sp2, so double triple bonds, then the reaction will not proceed. The second limitation of Friedel-Crafts alkylation results from polyalkylation. So if you have more than one site that may accept these groups, these alkyl groups or these carbocations, then they will take them. Third, some substituted aromatic rings, such as nitrobenzene, are too deactivated to react. Now, let's talk a little bit about Friedel-Crafts acylation. In acylation, you're adding an acyl group instead of an alkyl group. You can see the difference right here. That would be the carbonyl. So they both form new carbon-carbon bonds. The main difference being that carbonyl right there. That's pretty much it. Acylation reactions are also catalyzed by aluminum chloride as the Lewis acid. The active electrophile is going to be an acylium ion. See acylium ion right here. And the steps for that formation are exactly the same as the ones for your carbocation in your alkylation. So my advice, since both of these are so similar, if you know one, then you know the other. Acylium ions are resonance stabilized and not subject to rearrangement. For the acylation mechanism, this bottom part right here, we've already discussed a number of times. The top part, however, is very interesting because you see the attack of your halogen, or your chloride in this case, towards that aluminum, and you have the formation of your complex, which makes it a very strong electrophile. And then you have your resonance stabilized ion forming that will then trigger this reaction to proceed. Some alkyl groups cannot be attached to a ring by Friedel-Crafts alkylation because of rearrangements. An acylation followed by a Clemmenson reduction is a good alternative. In a Clemmenson reduction, as you can see, we add zinc, zinc mercury complex, hydrochloric acid, and then heat. Polyacylation is generally not observed, which is one of the limitations you get with alkylation instead. So that's actually a positive, right? That's something that we see as an advantage of acylation over alkylation. Now let's talk a little bit about electron donating groups. You see this shorthand as EDG. So let's start. Two issues arise when adding a group to a ring which already possesses one or more substituents. This is very interesting because now it's not just benzene, right? It's something else. So what happens when it's something else? For example, toluene here. I try to do a nitration. Will it happen? And if so, will it happen faster? Will it happen slower? Will it be any effect with the stereochemistry of the reaction? These are the things that we'll be trying to answer throughout this section. Toluene reacts much faster than benzene. The methyl group is electron donating, making the ring a better nucleophile. That should give you the first hint as to some of the general rules that we'll see in this section. Now, when we talk about regioselectivity, there are three possible products. When we're adding that nitro group, it could be ortho, meta, or para substitution. Now, let me tell you a little bit about this. When we say ortho is 1, 2, so in other words, the nitro group goes here in that 1, 2 position. Meta is going to be 1, 3, so here the methyl group, and then here the nitro, so 1, 3, and then 1, 4, that will be para position. You can see the scheme right here of your ortho, meta, and para substitution. Now you can see the yields, experimental values, they vary wildly between all three of them. So the ortho nitrotoluene that you would generate, right? The ortho is going to be the predominant product, followed by the para, and lastly, just a very small 3% of that meta substituted product. Now let's look at the relative stability of the sigma complex, an intermediate that we've been seeing throughout this chapter that may give us some clues as to why we have such different yields. Now, let's look at the 1-2 attack right here, the ortho attack. Now, when that happens, you have your methyl group right here, and you lose the electrons here, so your carbocation forms right here, which can then be resonance stabilized, so your positive charge lies here, here, and here. Now, when you look at the meta attack 1-3, then your carbocations resonance stabilized, you can see that the distribution is a little bit different, right? They show up in different points in the hexagon on that non-aromatic intermediate. In the para attack, you see the same thing. Now, when you look at the stability, remember that methyl group is actually electron donating. So if you have a positive charge close to it, then it actually stabilizes that positive charge because it is already donating strong electron density. The consequence is going to be that energy barrier is going to be different between the ortho, the meta, and the para. The sigma complex obtained from the ortho and para attack has positive charge delocalized adjacent to the electron donating methyl group, which is what we just saw on the past slide, giving a more stable sigma complex intermediate. If you look at that meta attack, that energy barrier, that activation energy is just ridiculous, right? It's very large. So even if it does happen, which it does to a very small extent, it'll be very slow. If you look at the para, the activation energy is much smaller, and if you look at the ortho, it's also much smaller than the meta attack. As a consequence, the ortho and the para products tend to predominate. Very little of the meta product is formed, only 3%. More ortho product is formed because there are 2 ortho positions and only 1 para position. So if you multiply this 34 by 2, it'll be 68, which is comparable to the 63. That's basically what that means. The methoxy group in anisole activates the ring 400 times more than benzene. The methoxy group donates electron density via resonance. So you can see here that the lone pair sort of moves and then generates that stabilization via resonance that we've seen so far. The methoxy group activates the ring so strongly that a Lewis acid catalyst isn't necessary, and polysubstitution is difficult to avoid. Activators are generally ortho-para directors. Now here are two terms that are very important and we'll see throughout the rest of the chapter. First is activators. Activators are groups that we see that when attached to an aromatic system sort of allow for a reaction to happen a lot faster than if it were just benzene, right? Benzene is our baseline, that's the one we're comparing. And every time you have a group that sort of makes things go a little bit faster, we call that an activator. The other term that is important is going to be directors. So ortho-para directors, ortho position, para position, and then you're going to see meta directors. So you're looking at two different phenomena, and we're sort of consolidating them into one set of predictables or predictors. The activators, that's a kinetic factor, and the directors, which is more of a regio-selective type rubric or idea. Like the methyl group, the methoxy group is activating an ortho-para director. Here, para is the major due to the ortho position being more sterically hindered. Now, steric hindrance will also play an important role in terms of those yields, right? We'll see that throughout the chapter. The bigger the group, the more likely one position is going to be favored over another. Resonance stabilizes sigma complex of ortho and para attacks. We saw that with the methyl group as well. Resonance stabilizes sigma complex of ortho and para attack, and consequence, just like for the methyl group, the meta attack has a much higher energy barrier to overcome than the ortho and para. Therefore, it is the least likely product to form. Now, when you have electron withdrawing group instead of electron dominating, then it's a little bit of a different story. The nitro group is an example of what we call a deactivating group. Now, if activating groups speed up the reactions, then deactivating groups will go the other direction. They'll make reactions go slower than if it were pure benzene. Remember, benzenes are baseline, so we compare against that. It is both inductively electron withdrawing and withdraws electron density from the ring via resonance. So that means that having a carbocation it's not going to be easy for benzene, right, or for that aromatic ring, because you have a group that is taking away electron density in a system that is already electron poor. So that's sort of what makes this deactivating group. Nitrobenzene undergoes nitration 100 times slower than benzene. And in this case, the meta product is going to be the major. There's no longer ortho or para, but you can see the numbers here. For ortho, it's going to be 6, for para, just 1%, and then 93% for that meta product. The reason, that's going to be, again, that sigma complex, where is it more stable? So in this case, having the positive charge as far away from that nitro group as possible, that's going to be your best bet. And that happens when you're in that position para to relative to that nitro group, or your ortho to it. Now, if you are in an ortho attack, you can see the positive charge right there. That's a horrible place to be, so that's not very convenient, especially for a electron withdrawing group. In the para attack, you have the same scenario. That leaves the meta as your favorite or most likely intermediate to be the most stable. The energetics are also going to agree with that. So you can see the meta attack has an energy barrier much smaller than for ortho and for para. In that case, like the nitro group is a deactivator, it is also a meta director, right? So again, activator, deactivator, that makes things faster or slower. And then the director term is the one that we use for indicating that that position where that group is going to be located. In this case, meta, that's the 1,3 position. Now, halogens are a little bit of an exception. Let's take a look at some of the general trends that we see. All electron donating groups are ortho-para directors, and all electron withdrawing groups are meta directors, except for the halogens. Halogens withdraw electrons by induction, so they are deactivating, that makes things go slower. they donate electrons through resonance. So they are ortho-para-directing. So typically, if something is deactivating, you would expect it to be meta-director. And if it's activating, you would expect it to be ortho-para-director. But when you talk about halogens, halogens are deactivator but ortho-para-director. So that's a very important exception. Make sure that you keep it in mind. Halogens withdraw electron by induction. We just covered that. They are deactivating and they are ortho-para-directors. And you can see the sigma complex. You see that stabilization. That's basically what allows for that ortho-para directing position to be. You can see ortho position, the negative charge is actually relatively favorable, and then that para position, ortho and para. Halogens donate electrons through resonance, so that actually makes things a little bit different than for other electron withdrawing groups. Let's say you're trying to add a nitro group, kind of like the one you're doing here, or the one we've been doing throughout basically the entire chapter. When you do that, you have the ortho, meta, and the para attack. And in this case, one of your intermediates, right, in your sigma complex is going to be where your chlorine has a positive charge, so this becomes neutral. And that is actually a relatively favorable position compared to just having that positive charge just moving around like you do in the meta attack. Now, a couple of groups here that we can start sort of categorizing or start cataloging everything. We have strong activators, we have moderate activators, and now this relative strength that we're talking about has a lot to do with how fast things go. So a moderate activator will speed things up, but nowhere near as much as a strong activator. We're also going to be talking about weak activators. They speed up, but again, not as much as your moderate or as your strong activators. All of them are ortho-para directed. So this is a good time for you to sort of look at this slide, familiarize yourself with the different groups, so you can start making predictions, right? Make things a little bit easier rather than just having to draw out the entire sigma complex and figuring out the energetics. If you know these groups, then that sort of makes things a little bit easier. And these are your weak activators. And again, they're being ortho-para directed. Now let's take a look at the deactivators. We have very strong deactivators. These are groups, remember they're electron withdrawing. They're going to be meta directors, except again, they're halogens. They're deactivators, they're actually a little bit on the weak side. They're ortho-para directing. Remember, the halides are the only deactivating groups that are ortho-para directors, as we've mentioned a number of times. Now, let's talk about having more than one substituent. What happens when you don't have just one, right? You have multiple substituents. Well, what happens is that the directing effects of all substituents attached to a ring must be considered in an electrophilic aromatic substitution reaction. That's where relative strength actually comes into play. We'll see that in the next couple of slides. The directing effects of the methyl group and the nitro group direct the bromine to the same carbon. In that case, it's easy peasy, you get just the one product. This is ortho-para directing, this is meta directing, which happen to be in the same position. So that's actually ideal. If the group direct to different carbons, then the stronger group will dominate the directing effect. That's where you get your strongest yield. That's why we talked about strong, moderate, and weak. So here, for example, we have a strong activator, and it is ortho-para, so it'll be either here or here. And this is a weak activator, ortho-para, so it'll be here or here. So we're talking about either these two carbon atoms or these two carbon atoms. Because the hydroxyl group is a strong activator, then the nitro group is going to go here, as you can see. Another important and practical aspect that we need to consider is going to be steric hindrance. Steric hindrance must be considered when more than one product is possible, using some of the guidelines that we'll sort of delineate here. For a monosubstituted ring, the para product is typically the one that dominates, simply because it's easier due to steric hindrance, right? It's easier to accommodate something in this position than it is in this position because of the large electron cloud we have hanging over here. For 1,4 disubstituted rings, substitution will occur at the less sterically hindered site. if more than one site is favored by directing effect. So here, for example, you could have orthopara, so these two, or orthopara, these two. Here, this is more sterically hindered, right? Sterically hinders the process, so that means that the likelihood is that the nitro glue is going to be added in this side. That allows for this to be your major product and this to be your minor. So it's not zero, but it'll be in the minority. For 1,3 disubstituted rings, substitution typically does not occur between the existing substituents. So in other words, something that may be substituted here for all practical purposes, this doesn't happen. So what you will see is substitution on this side, depending on whoever's the least steric hindrance. That's going to be your major product, just like we see here. Considering how one might force a substituent to add ortho instead of para in the presence of an ortho-para director. In that case, you can add what we call a blocking group. A blocking group could be used to prevent substitution at the para position. So something that is, for example, something that is massive, that's big, right, steric hindrance, that actually could act as a blocking group, just to give you an example. Sulfonation, since it is reversible, is commonly used as a blocking group. So the synthesis can be accomplished as follows. So for example, here I have my terbutyl group. I want to add the bromine, but I want it in my ortho position instead of para. But if I just go straight to that substitution, most of it will go into my para position. So I need a blocking group right here in that para position. So sulfonation. Once I have that para substitution, then I proceed to do my bromination. And because the sulfonation is reversible, once I'm done, once I have my product, then I get rid of my sulfide group. That's it. Now let's talk a little bit about synthesis strategies. How do we go about generating products depending on where I'm starting and where I want to finish? 10 different groups can be installed on a benzene ring using the reactions we have covered so far. You can see our halogens, our nitro, our sulfonation, methyl, and acyl groups. From there, we can then proceed to add a second set of groups, as you can see here. So that means that we have a rather generous amount of substituents that we can add to a benzene ring, to an aromatic. Here, the most important part of the multi-step synthesis or synthesis strategies, as we call it, is to sort of sit down and sort of think about what kind of product you want and how you're going to get it, based on whether your group is activator, deactivator, and the directions. Synthesis of disubstituted benzene rings require careful analysis of directing effects to decide which group to install first. So in this case, I want to add a bromine, also want to add a nitro. And I know that a halogen, for example, is going to be an ortho-para director, but I know that nitro is going to be a meta director. So in this case, if I add the nitro first, then the substitution at the meta position to the bromine will actually be favored. Right? I don't have to fight against those likely orientations. So it makes sense to install the nitro group first. So that is important in terms of sort of us having an idea of what type of directing effect and functional groups, right, are associated with these effects. Additional consideration is necessary when one of the groups require more than one step to install. So for example, here I'm adding chlorine, right, a halogen, but I'm also adding an amine. As you remember earlier in our conversation, amines are actually added by adding first a nitro group and then reducing that nitro group. So groups need to be meta, but both substituents are ortho-para directors. So that's sort of a challenge here, right? So I need to add the amine, but for the amine, I need the nitro first. Recall that adding amine groups require nitration and then reduction, kind of what we see here. So what needs to happen? So I know that amine is an ortho-para director, and so is chlorine, but nitro is actually a meta director. So What I can do, I can add my nitro group first, and then I add my chlorine, and after I add that chlorine, then I modify my nitro into an amine. But I can't do any of that if I don't know that the nitro group is a meta director and chlorine is an ortho-para director. So these are things that you have to familiarize yourself with in order to successfully synthesize these types of products. Other limitations that must be considered when planning a synthesis: nitration cannot be done on a ring that already contains an amino. So that means that if you already have an amino, you can add a nitro. Redox reactions don't work on a ring that is moderately or strongly deactivated. This is an energetic type of process. So that's just something to consider as well. Now, let's talk a little bit about nucleophilic aromatic substitution, or SAR. Nucleophilic aromatic substitutions are reactions where the benzene is attacked by a nucleophile. So far, we've only discussed electrophiles, so it's going to be the other side of that coin. So here, for instance, a hydroxyl is the nucleophile, and bromine will be acting as the leaving. Three requirements, or three things that need to happen for nucleophilic aromatic substitutions to take place. First, the benzene ring must possess a strong electron withdrawing group. Second, the ring must possess a good leaving group. And third, the leaving group must be positioned ortho or para to the withdrawing group. If the leaving group and withdrawing group are meta, the reaction doesn't happen. With the electron withdrawing group in the meta position, it is unable to stabilize the Meisenheimer complex intermediate. So let's take a look at that. The Meisenheimer complex, which is another term for resonance stabilized carbanion instead of carbocation. So this needs to be stable. As you can see here, the mechanism or the mechanics of it are very similar to our aromatic substitutions, our electrophilic. You have a nucleophilic attack, you have a deprotonation. Now instead of a carbocation, you actually have an electron pair that is going to be resonance stabilized, the form of carbanions. And then you get the loss of the leaving group and return of your aromaticity. So the steps are fairly similar. The substituted phenyl group is deprotonated under the basic hydroxide conditions. So acidic workup is necessary to obtain a neutral organic product. So in other words, if I'm removing my good leaving group here, my bromine, and forming a hydroxyl, I will actually form the negatively charged, right, the deprotonated species, which I would then need to neutralize and acidify slightly so that I can form the hydroxyl group. Recall that these type of reactions will not happen if the ring doesn't have a strong electron withdrawing group. So just because I have the conditions does not mean that the reaction will take place at all. But if very high temperatures are used, then a reaction will occur. So I have to sort of force it that way. If you look at these temperatures, right, this isn't something that's going to happen with just any solvents. I need to be very careful because 350 degrees Celsius, most solvents will actually evaporate at that point. The reaction works even better and doesn't require high temperature if a stronger reagent is used. The regiochemical outcome means this reaction does not proceed to an SNR mechanism. Using an isotopically labeled substrate, it is clear that substitution is occurring at two different carbons. So you can see here, you actually have the substitution happening both here and here. And this can be due to the fact of the benzene intermediate. This is a species that you can see here that have a triple bond inside of your benzene ring. Nucleophilic attack by the amine anion can take place at either carbon of benzene, followed by protonation of the other. And in that case, then you actually have two sites, which means that you will get those two products. This is an elimination addition mechanism. Let's take a look at it. Elimination addition mechanism, you have a deprotonation step, you have the formation of your carbanion, you lose your leaving group, and then you get the benzene intermediate, then you get your nucleophilic attack, followed by your protonation, and you get your final product. So the mechanism itself here and the postulated benzene are a little bit more complex than you would expect to see from a carbocation instead. That's what makes this a little bit different. That's why we actually separate both reactions when we're studying them. Evidence for the formation of the benzene intermediate comes from a trapping experiment. Small amount of Diels-Alder product is obtained if furan is added. We actually form a cycloadductor reaction through Diels-Alder. This flowchart can be used to identify proper substitution mechanism. In other words, this is just sort of a simplified version of a summary of what we've seen so far. And from there, you can then decide specific groups, activator, deactivator, and then orientation as well.